Which statement is more correct? When playing the iterated prisoner's dilemma, minimax is a poor strategy or is it the best strategy? This one was kind of a, did you show up to my lectures? That one's the answer. It's not a great strategy. Turns out tit for tat is a really great strategy for iterated prisoner's dilemma. And you can actually compute that with utility theory if you use an altruistic measurement of utility. If you use a self-interested measure of utility, it turns out that doesn't make good cooperative choices, as one would expect. And so that was the answer. Consider the following two-player zero-sum turn-taking game. I made a mistake. This was not a zero-sum game. And I shouldn't have said that. That's because I copied and pasted from a previous test and that word leaked over. If you were thrown off by that, you have something you can talk to me about as far as bickering for points on this question. Let's do this game. Yes, it's a silly game and it has a lot of rules. There they are. I'll assume you've read them and not read them to you again. Is that okay? Basically, here's what the game looked like. There were 4 marshmallows on the table. Every single turn, you can make one of 2 choices. You can eat 1 marshmallow or you can eat 2 marshmallows. That's it. Those are your only choices according to the wording of the problem. Player 1 can either eat 1 marshmallow or 2. Let's suppose player 1 is represented by the color blue. We'll do blue versus red because that's pretty standard. So player 1 can either eat 1 marshmallow or 2. Okay. Well, let's suppose that player 1 ate only 1 marshmallow. Then it's player 2's turn, right? And what should player 2 do? Well, or what can player 2 do is, I guess, the real question I'm asking. Player 2 can either eat 1 or 2 marshmallows, right? So player 2 could either eat 1 or 2. And if we go this option, player 2 could eat either 1 or 2 marshmallows. With me so far? Okay. Well, right here, that's the end of the game. All the marshmallows are eaten. Right here, that's not the end of the game because the next player has to go, and the next player is going to be player 1 because it's a turn-taking game. Did I use the words turn-taking anywhere? Turn-taking game. Okay, good. All right. Well, if it's a turn-taking game, then who has to eat the last marshmallow? Player 1. Okay. And player 1 has to eat that one again because it's player 1's turn. But in this one case, there are 2 possibilities. I did indeed. In fact, nobody made it colorful like this, and that's totally okay. You throw marshmallows at the dog. The game does not indicate that's allowable, so I think the answer is no. The real part of the question that I was trying to get at is, can you evaluate this thing? And the way the question asked you to evaluate it was, indicate the score for both players at each leaf node. Each player's score is computed as number of marshmallows they ate minus the number of marshmallows their opponent ate. A minus B. Plus, the last marshmallow is worth 5 extra points for the person who eats it. Okay, so it's just a matter of let's compute the score at all the leaf nodes. Here's a leaf node. I ate 2, or player 1 ate 2, the other player ate 2. 2 minus 2 is 0. Who ate the last marshmallow?
Player 2.
Player 2, red. So the score will be 0, 5. This one, and all of these ones, player 1 ate the last marshmallow and will thus get 5 bonus points. So the score here, well, we'll do this one on the left. 3 minus 1 is going to be 2, plus 5 is 7. What is 1 minus 3? Negative 2. Okay, and this one's going to be 5, 0, and this one's going to be, what's that, 7 minus 2. And the final score of this leaf node way down here is 0 and 5 because player 2 got the bonus points. So there you go. You have the score for the leaf node. And, you know, what's the value of this? I don't know. It was one of those nasty, just did you read the question super carefully questions. And I hate those. But it was really about, can you understand how to break down a game into a tree of possibilities? Because that's an important thing in AI. so you can analyze it properly. And the next few questions are all about analyzing it. At each node in the tree, embolden the branch that represents the choice. A lot of people just wrote over the line once more with a pencil, and it was really hard to tell which line had been emboldened. Okay, let me emphasize. At each node in the tree, embolden the branch that represents the choice the player will choose. All right, so the only way to do this really is to start at the bottom. Those of you who tried to start at the top, you kind of didn't get what was going on. Because at the bottom, you have the scores, right? Okay, which choice will player 1 make right here? That one. It's the only option. And that choice will be made, and that choice will be made, and that choice will be made. So all of those should have been emboldened.
Yeah, that one's not a given.
Oh, that one's not a given. You're right. I take it back. We'll discover why in just a minute. Okay, these are all the ones where that was the only choice, so of course you're going to choose them. Okay? Now, how about right here? Which choice should player 2, nope, it's not player 1, it's player 2 that gets to decide which future they want, because this is the present if these are the futures. So which of these two futures will player 2 choose? Player 1 gets to choose to make this choice. Okay, the choice is the branches. So this one is lined up right there. This one is lined up right there. This one is lined up right there. This one is lined up right there, and that's what you were telling me. Okay, got it. Yes, and that matches the numbers I picked. Okay, question is, at this moment, player 1 gets to make this choice. Which choice will player 1 pick? Well, the answer, the game says, okay, assuming that each player will play only to maximize his or her own personal score. That's the key to how you should evaluate this. Player 1 only cares about his score. In other words, player 1 will look at, do I want a 0 or do I want a 7? Which does player 1 want? 7 is more than 0. Notice I didn't consider player 2's score as one does in Minimax. Incidentally, we'll do Minimax on this just to show you what happens, but player 1 would choose that one. Okay, well, so now the utility for player 1 of being here is 7. Utility of player 1 for being over here is 5. But player 2 is the one who gets to make this choice. Does player 2 want 0 or which way will they go?
Well, -2 is guaranteed.
-2 is guaranteed because they already know 1 will make this choice. Therefore, player 2 gets to choose between a utility of -2 and 0. Which one does player 2 like?
0.
Player 2 will, of course, prefer 0 over -2, so this branch should have been emboldened. What about over here? This one's also player 2's choice. Does player 2 prefer -2 or 5? 5 is better than -2. Okay, so finally, player 1 gets to choose between a universe in which it gets 5, right there, or a universe in which it gets 0. Notice there's only 2 possibilities. You don't have to run down to all the other branches because its opponent will never choose it. Obviously, player 1 likes a 5 better, so player 1 picks this branch. If you embolden those branches, that was the expected answer on that problem. Okay. What will be the final score? He'll make this one, then this one, then this one. That's the final score right there. Anyway, we'll see. The final score here should have been a 5-0. And you really should have said P1 gets 5, P2 gets 0. What happens if you prepped on Minimax instead of this thing because you assumed everything's Minimax? Because it seems like a competitive game, doesn't it? How do you do Minimax? If you add them together, notice something. 0 plus 5 is 5. 7 plus -2 is 5. 5 plus 0 is 5. 7 plus -2 is 5. And 0 plus 5 is 5. Looks like a constant sum game, doesn't it?
No.
It's not. It looks like it, but it's not. What's a constant sum game? Constant sum game is where the utility always adds up to a constant. And it turns out minimax is the optimal strategy for zero-sum games as well as constant sum games. Minimax is not necessarily the optimal strategy for this game, but it just happens to be for this game. That wasn't super clear. But here's the deal. When you do minimax, you don't add the utilities together. You take one utility minus the other. So this one should have a utility of 0 minus 5, so that's a negative 5. What's 7 minus negative 2? 9. 5 minus 0 is 5. 7 minus negative 2 is 9. And 0 minus 5 is negative 5. Okay, so these in green circles are the minimax outcomes. And what happens if you do minimax? Well, P1 is the maximizing player because I did player 1 positive and player 2 negative. And it turns out if we do it with minimax, then, well, all the leaf nodes choices are made because they have to be. Which choice does player 1 like here? The 9, that one. Which choice here?
The negative 5 over the positive. Minimizing player.
This is the minimizing player, so it's going to choose that one. Which choice here? Your choices are, this is the minimizer, and you can get a 5 or you can get a 9. Choose that one. Okay, so does the maximizer want a 5 or a negative 5? Wants that one. Turns out if you do minimax, you get exactly the same solution, but only because of the way it works out. Because these do not add up to a constant sum, it's possible to have games where minimax doesn't produce the same answer as maximize your own personal utility. So it's important to note what strategies players are using. Minimax is the strategy intelligent players will use in competitive or constant sum games. And this one wasn't exactly a constant sum game. There could potentially be situations where you'd think, hey, if we do this, you can have the marshmallow bonus and I can have the points, and it's to our advantage to choose something that's not necessarily competitive. It just didn't play out that way because I didn't want to create a great big controversy on the test. I probably should have, just for learning experience. Okay, can A* search offer computational improvements over breadth first search? Yes, it can, for reasons stated in the test review of last test. Okay, single point crossover. This one is one of those did you pay attention technicalities. What you do in single point crossover is you pick a point anywhere, let's pick right there, and you cross over. So before you were doing this one and then you're doing that one. So if your answer was Kataga at Guttag, that was a valid answer. Or if you crossed over anywhere else, that was fine too. Some things that single point crossover are not are crossing over lots of times. That's multi-point crossover. And it's not just switching two of them, which is, although I can see why based on the wording of single point crossover, you might do something like that. But that's not what it is. Single point crossover is pick a point and crossover at that. Technically, yes, because the point could have been right there. So if your answer was just that one, that's full credit too, technically. You would have had me on a technicality. I'd have to give it to you. Okay. Time. Gotta go fast. Why does random forest use trees that make random divisions? Random divisions cause trees to be more inconsistent with each other. Why do you want that? Better ensemble. Okay. How does bagging work? It trains each model with the same data, but no. Trains each model with data that has been resampled with replacement. Then gives each model one vote in the final prediction. Number 12. The tree below represents a zero-sum turn-taking game. The branches that would be pruned by alpha-beta pruning, if the choices are evaluated in left to right order, are already marked. Please draw an X on the branches that would be pruned if choices are evaluated in a right to left order instead. Part of my intention with this problem was, hey, if you didn't fully study it, at least now you could sit there on the test and figure out how the heck alpha-beta pruning works and then use that to turn it around and do it the other way. And that way the test is more of a learning exercise than a testing exercise, which is the way I think it should be. Don't know if did anybody actually figure out alpha beta pruning on the test? No one would admit it, but if you did, that's awesome. You reaffirmed what you knew. Oh, that's good. Okay, so, well, let's do it backwards now. We'll do it in blue. So, first of all, are you aware that if you run down the branch, there's no way that anything will ever be pruned on the very first branch? Why? Because how could it? You don't know anything yet. So we cannot prune there. We cannot prune here or there or there or there. But wait a minute, why is that one pruned? Because they're doing it the other way. You notice nothing on the left side is pruned. Okay, so nothing is there is pruned. The first chance we have an opportunity to prune would be this one right there. Do you agree? Because that's the first time we visit it. Is there any reason we should prune that particular node? Well, so far we know we have a 6 up here, right? What if it were a 7? Then this guy would take it because he's the maximizer, right? And we don't know anything else higher up. I think that cannot be pruned. We go down here, we get that 5, we pull it up here. What about here? Can we avoid looking down here to see that 8? I claim that we can. The reason is, hey look, we already know we've got a 5. If we get something better than a 5, like say a 4, then the minimizer would take it. But if we did, its parent, which already knows it can get a 6 from this branch, would not accept a 4. So we're wasting our time trying to improve this node. Therefore, we prune this branch. There you go. And we come back up. Nothing else can be pruned so far. What about this one? Can that one be pruned? Why not? Because this is the minimizer, and we know we got a 6, but hey, what if this were, say, a 5? And in fact, it is a 5. So this is one thing that kind of cracked me up on the test on grading, is when people prune something that would have changed the results. The whole point of alpha beta pruning is it shouldn't change the results. So if you prune something that would have changed the results, then clearly that's wrong. Big takeaway, if it's going to change the answer, don't prune it. If it could change the answer, don't prune it. Does that mean alpha beta pruning is going to prune everything that doesn't or couldn't change the answer? Not necessarily. It doesn't do deep reasoning. It just does this one logical comparison. So if we come down here, we come down there. If we say prune this one, does that change the answer? Yeah, so obviously you don't. What about that one? Well, if we're even coming down this branch, we need something. So we're going to pursue all the way down to the end and get a number. So nothing along here can be changed. We come down here, and can we prune this branch right there? The answer is no. Why not? Because we're the minimizer, and hey, what if it were a 5? That would be better than this 7 we've got, right? Or what if it were a 6? In fact, it is a 6. By demonstration, this proves you can't prune that one, because that one actually is used. Can't prune this one, or that one. What about this one? What if we get higher than a 6? Like this is the maximizer, right? This one could, in theory, be, say, an 8. And if we got an 8, that would be great. But we know our parent won't accept anything better than a 7, because our parent so far knows about this 7. So can we prune it? This one's an interesting question. It turns out that alpha beta pruning won't prune it, because alpha beta pruning doesn't know that they have to be integral values. Meaning, if it were a 6.5, that would actually be better than this 6 we've seen here, right? So hey, 6.5 could be better, and yet that would still, the minimizer would choose 6.5 over that 7. And so because a 6.5 is a possibility down this branch, we can't actually prune that node. Now we have extra knowledge that these are all integral values, there are no decimal places, but alpha beta pruning doesn't do that. If you had that knowledge, you could actually encode in your alpha beta pruning implementation a +1, meaning if alpha plus 1 is greater than or equal to beta, then break. And you could actually make it slightly more efficient and prune slightly more, and this is the one case that demonstrates that. But the alpha beta pruning algorithm does not prune that, or this. So no pruning. We keep going. Can we prune this one? No, you never prune anything at the root level. Can't prune that one. We run down here. Can we prune this branch right there? This is the minimizer. So far we've got a 3. Well,
Yeah.
what if we found something better, like say a 2? Then this node would accept it, but its parent would say, hey, wait, I've already got a 6. Why bother? Therefore, the answer is yes, we do prune that node. And if you prune that node, you don't have to go and prune all the nodes underneath it because, hey, the whole point of pruning is not to waste your time visiting that branch. So it wouldn't be correct to do all that. It should just look like this.